Greetings, my name is Pedro Brito and I'm very glad to be here today to give this talk, which is entitled On the Effect of Pre-Strain on Hydrogen Embrittlement Susceptibility of Structural Steel. This work was conducted at the Pontifical Catholic University of Minas Gerais, and is being presented here at the 26th International Congress of Mechanical Engineering, COBEM. So a brief introduction. Structural steels are widely used in port infrastructure, which includes marine structures, pipelines, sea vessels, offshore structures. And in these conditions, these steels are subject to environmental degradation. The most visible problem is corrosion. But associated with corrosion processes, we can have the absorption of hydrogen atoms in the material. The possible mechanism for this is the known effect that near a crevice or a gap on the metal surface in which the electrolyte is constrained, there can be an acidification of the electrolyte, so an increase in the concentration of hydrogen ions. And when these hydrogen ions increase their concentration, they can become absorbed. They tend in the material to concentrate in the vicinities of crystal defects, such as vacancies or dislocations, and by different mechanisms, this absorbed hydrogen can induce a loss of ductility and a loss of mechanical strength. So, based on these premises and based on the fact that structural steels are used in a variety of conditions, we proposed to analyze the influence of preliminary plastic deformation or pre-strain on the susceptibility to hydrogen embrittlement of a structural steel, a common 1020 steel, low carbon steel. Specifically, we aimed to evaluate the influence of cold work produced by uniaxial tension on the mechanical strength of this low carbon steel, then to analyze the hydrogen permeation behavior by cathodic charging of the steel in different solutions, and finally to evaluate the influence of hydrogen on the mechanical strength and the ductility of the selected steel. So the details of the experiments. So the material used were these 1020 low carbon steels. We prepared tensile test specimens with a 67 millimeter length and 9 millimeter diameter of the gorge section. And these materials were initially annealed. They were received in the hot rolled condition, so they were annealed. And then they were subject to 0, 6, and 12% of preliminary plastic strain. So these levels of strain were introduced after yielding. These were performed by uniaxial tension using a universal tensile testing machine. After this, hydrogen was permeated in the materials in two solutions: a 0.5 moles per liter acid solution, or sulfuric acid solution, and a 0.6 moles per liter sodium chloride solution. In both cases, 0.25 milligrams per liter concentration of a recombination agent was used, and in both cases also a 30 milliamp per square centimeter current density was used, and for exposure time of 24 hours. We have here some pictures of the setup. Samples were protected by insulation tape to avoid contact of the hydrogen source with the entire cross section, and only a small section to be exposed. Before and after permeation, samples were measured in order to guarantee that no loss of mass or no corrosion occurred in the process. But since it's a cathodic polarization, no corrosion is expected to take place in this situation. So in this graph, we just illustrate the procedure for determining the preliminary strain levels. So we have here a tensile a force displacement diagram for the annealed specimen, and we see the point of yielding, and after yielding we selected the two displacement levels, one of 4 millimeters and second of 8 millimeters after yielding, to which we would strain the samples and then to evaluate the behavior concerning hydrogen absorption. Stress levels were chosen so as that we would not go over the ultimate tensile stress point. After these pre-strain, after the samples were pre-strained, we conducted microstructure and microhardness assessments to verify whether any significant change in microstructure took place. We found that concerning microstructure, nothing significant happened. In all cases, samples they consist of ferrite and pearlite colonies. And concerning the hardness distribution, we see no significant trend concerning hardness in the center and the surface of the samples, but we do see an increase in hardness as we increase the level of pre-strain as expected. Here we see the influence of hydrogen on the mechanical properties, on the tensile strength of different samples. And here we tested 2 electrolytes. So for the annealed sample, so 0% pre-strain, the results are shown in letter A. We compared only the no charging situation and the charging in acid solution. For the remaining cases, in letters B and C respectively, we compared the acid solution with the sodium chloride solution. What we can see is that there is a definite influence of hydrogen, and this influence increases with the amount of pre-strain. So a small loss of ductility is noticed for no pre-strain, and this gradually increases as we increase the level of pre-strain. It's also possible to notice that the acid solution, possibly because of the larger availability of H+ ions, is a more severe electrolyte concerning the absorption of hydrogen and consequently the embrittlement of the material. The results of the mechanical property examinations are summarized here. We can see that there is an increase in yield strength and tensile strength with the level of pre-strain, but the hardness of the sample or the mechanical strength itself is not affected by hydrogen. We can see here by the first graph in which the values concerning mechanical strength are the same with and without hydrogen. What the hydrogen does, however, is reduce the maximum elongation, consequently the ductility of the material. Here we see a drop in ductility for all cases, and more severe in the acid solution. It's also relevant to notice that for the larger amount of pre-strain, so when the samples are pre-strained to 12%, all samples exhibited more or less the same ductility, meaning that it appears that after a certain point of pre-strain, hydrogen does not further decrease the ductility of the material. We can see this when we look at the 12% pre-strain results, and all samples have the same ductility. So to summarize and to conclude, in this investigation we submitted low carbon 1020 steels to different sources of hydrogen, and we observed the following. The acid medium was more severe regarding embrittlement than the neutral medium. The charging process performed on all materials did not alter mechanical strength, but did impart in loss of ductility. And for higher levels of plastic strain, 12% post-yielding, no significant decreases in ductility observed, regardless of the charging conditions. In this work, we were supported by a mining company, Vale S.A., through the project Cátedra Equipamentos Portuários, so knowledge support from Vale,